Section 7.2 is exponential change and separable differential equations. When we were solving the initial value problems in section 7.1, what we were doing was kind of like solving separable differential equations. They're the easiest differential equation to solve. And you can recognize a separable differential equation problem if you have dy dx equals a function of both x and y, where f is a function of both the independent and dependent variables. A solution of this equation will be a differentiable function y equals y of x defined on an interval of x values, perhaps infinite, such that the derivative with respect to x of y of x is equal to f of x y of x on that interval. Basically what it boils down to is if you have dy dx equals a function of x times a function of y, you can separate this so that dy dx is equal to g of x over h of y. So if you rewrite this equation in this form where dy dx equals g of x over h of y, you can then cross multiply and set up this equation h of y dy equals g of x dx. Then integrate both sides of the equation and solve for y. And that's how we're going to approach these problems. Let's just work through a couple of these problems and you can see how they're done. In example 1, we're asked to solve the differential equation dy dx equals 6e to the x minus y. Recalling your property of exponents, if you have subtraction in the exponents, how can I rewrite this? I could rewrite this as e to the x divided by e to the y, couldn't I? Because when you divide with a common base, you end up subtracting the exponents. Do y'all remember that property of exponents? Okay. When we cross multiply now, that's going to give us dy e to the y is equal to 6e to the x dx. Now we can integrate both sides of this equation. And when we integrate e to the y dy, I guess I should have written it e to the y dy. But when we integrate this, what are we going to get? Just e to the y plus some arbitrary constant equals, when we integrate 6e to the x, we get 6e to the x plus some arbitrary constant. Now, because these are arbitrary constants, I'm going to combine these and write them on one side of the equation. And what I end up with is e to the y equals 6e to the x plus some arbitrary constant. The goal, though, is to solve this for y. So how do I get that y out of the exponent of e? What can I do to both sides of the equation? Take the natural log of both sides. So what I'm going to do is I'm going to take the natural log of the left-hand side and set it equal to the natural log of the right-hand side. And when I do that, that's going to give me the natural log of e to the y equals the natural log of 6e to the x plus c. So the left-hand side becomes just y equals, and then I have the natural log of, can I separate this? Can I distribute a natural log across addition? No. If you'll recall your properties of logs, we have a property that says if you have the natural log of a product, you can rewrite that as the sum of two logs. But if there's addition in the argument like there is here, there's nothing you can do to simplify that. This is just going to be the natural log of 6e to the x plus c. And that would be your final answer. You've solved the separable differential equation because you've got y by itself and y is a function of x. So let's just go through the process once more. Whenever you're given a differential equation, you want to rewrite it. If you have dy dx, you want the x function on top, the y function on bottom. Cross multiply to set up an equation. Integrate both sides of the equation and then solve for y. Those are the steps you're going to go through. Let's look at another problem. In this problem, I want to rewrite this without the radical. So I'm going to write dy dx is equal to 10x. I want the 10x on top. What would I write this as if I put it in the denominator? This would be 4 minus y squared raised to what power? 1/2 if it's on top, because the 1/2 takes care of the square root. But I need it in the denominator so I can cross multiply. So what do I do to the 1/2? It's going to be a negative 1/2. Now when I cross multiply, I'm going to end up with 4 minus y squared raised to the negative 1/2 dy equals 10x dx. This negative 1/2 stays a negative 1/2 when you cross multiply. What made it negative was the fact that it moved from being up in the numerator to the denominator. When I cross multiplied, it's up in the numerator, but how it got there was by being raised to a negative 1/2 to begin with. That has the potential for getting confusing. What's my next step going to be? Right, we integrate both sides of the equation. You're allowed to do basically anything you want to an equation as long as you do the same thing to both sides of the equation. I'm going to rewrite this left-hand side of the equation as the integral of dy over the square root of 4 minus y squared. And then we're going to set that equal to the integral of 10x dx. The reason I want to write it like this is because when you were in Cal 1, you should have worked problems with inverse trig functions and integrals. So if you will recall, the integral of dx over the square root of 1 minus x squared is equal to sine inverse x plus c. Do y'all remember seeing something that looked like that in Cal 1? For now, this is the only way that you can integrate these problems. In Chapter 8, I'm going to teach you a technique of integration called Trigonometric Substitution. It will negate your need to memorize these integrals for the inverse trig functions. For now, we're going to do it this way. I won't give you a problem like this on your first test where the integral ends up being an inverse trig function, but I will on your second test because I'm going to teach you a much easier way to integrate these problems than what this is. But for the time being, this is what we're working with. With this pattern that we have for inverse sine, I think that that's what this is going to be because I have a differential, I have a square root in the denominator, I have a constant minus a variable squared. The difference is this constant is 4 and in the pattern here it's 1 in the original problem. So what I need to do is I need to rewrite this or algebraically manipulate this so that that 4 will look like a 1. And here's how I'm going to do that. I'm going to do some scratch work. I have 1 over the square root of 4 minus y squared. If I factor a 4 out of that denominator underneath the radical, that's going to give me a 1 right here for this first term. And there's no 4 on the y squared. So what I'm going to do to counteract that is I'm going to rewrite this as y squared over 4. Now notice, if you were to distribute this 4 back across here, you would end up with the original problem. Agreed? So I can pull a 4 out of that y squared. I just got to put that y squared over 4. When I do that, that's going to allow me to rewrite this radical as 1 over the square root of 4 times the square root of 1 minus. Now that y is squared, I could rewrite the 4 as 2 squared, and that's going to give me y over 2 squared, which means that this will be equal to 1/2 times 1 over the square root of 1 minus y over 2 squared. That's how I'm going to rewrite this integrand over here. So that's going to give us the integral of dy over, that 1/2 is a constant that I can pull out, and then we get the square root of 1 minus y over 2 squared equals, I'm going to go ahead and integrate this side. And the integral of 10x is going to be 5x squared plus c. But to integrate the left-hand side, I'm going to need to do a u substitution. What can I let u be equal to in this problem in order to make it fit this pattern? I could let u be equal to y over 2, can't I? Another way of writing y over 2 is 1/2 y. So when I take the derivative of that, what am I going to get? 1/2 dy. Well, look at what I have here. I have a 1/2 and I have a dy, and that's going to get replaced with du. So I can rewrite this left-hand side as the integral of du over the square root of 1 minus u squared. And this is still equal to 5x squared plus c. When I integrate du over the square root of 1 minus u squared, I'm going to get sine inverse u. So this is going to be equal to sine inverse u plus c equals 5x sub 2 plus c. Since these are arbitrary constants, I'm going to go ahead and combine them, move them over, and keep that plus c on the right-hand side, which means this is what I've got on the left-hand side. It's just sine inverse u. But I've got to put the y back into the problem, so this ends up being sine inverse y over 2 equals 5x squared plus c. In solving these separable differential equations, our goal is to get the y by itself. Well, that y is trapped inside the argument of a sine inverse. How can I get that y out of a sine inverse? What undoes sine inverse? When you compose a function with its inverse, you get out what you put in. Do y'all remember that from algebra days? Like squares and square roots are inverse functions. When you take the square of a square root, you get rid of the square and the square root. So this is going to give us sine of sine inverse y over 2 equals sine of 5x squared plus c. So the sine and the sine inverse cancel out, and we're left with y over 2 equals sine of 5x squared plus c. To get the y by itself, I'm just going to multiply both sides of this equation by 2, and that's going to give me y equals 2 sine 5x squared plus c, and that would be our final answer. Okay, well then that wraps up section 7.2.